For those of you not familiar with ModalAI, we are a manufacturer of NDAA compliant and Blue UAS list components. So we make flight controllers, sensor stacks, software stacks, camera modules, electronic speed controllers, all of the components that go into typically multi-copter drones. But we make all of it here in California. Everything's NDAA compliant. And we spend a lot of time optimizing around Qualcomm chipsets and trying to extract as much compute power for as few watts and grams as possible to try and shrink things down just absolutely as small as possible. So we do make some drones, but they are reference designs for you to be an engineer, to experiment and design new algorithms. So I'll pass this little guy around. This is the first ever Starling 2 that was ever built. It's still the one that I develop with day in and day out, so I'll let you pass that around the room. That's also the unit that I captured all the pictures and videos in the presentation on. So this little guy has 5 cameras on it, 3 of which are global shutter 1 megapixel computer vision cameras for GPS denied navigation. And so what I want to talk to you about today is all the hardware acceleration that we've done to smooth out that image processing pipeline and create something which for under 3 watts of power can navigate around indoors without GPS. So obviously, this is a Qualcomm chip. This is the equivalent of a Snapdragon 865 that you would see on like a OnePlus 8 or a Pixel 4, I think, about that generation. And so it has the massive Qualcomm ISP in it, which will let you do all of the very pretty pictures that go up on YouTube and Instagram to make your face look perfect as if you were 20 years younger. But that ISP is very, very complicated, and you have teams of hundreds of people within Samsung optimizing out every single stage of the logic tree to decide how to adjust contrast in different parts of the image and adjust the white balance automatically. And we know how to do this, and we do use it for video streaming. However, it's not very well optimized for computer vision. Luckily, the Qualcomm image pipeline does give you a couple of little hooks to get in at a very low level. So for example, right at the camera imager front end, CAMIF, memory can be copied straight out into the application processor accessible RAM. This is something we'll talk about a lot, is that different parts of the memory bus on such a big chip actually are dedicated to different processors on the chip. We have 4 or 5 different DSPs on this chip. There's a massive GPU that's bigger than the 8-core ARM. We've got the 8-core ARM processor. There's a Sensors DSP, which is running the PX4 flight software stack off on its own little low-power island. And so the giant memory bus that runs through the system on chip is set up such that there are little hooks in and out of certain parts of the chip, which are very, very power efficient and very, very low latency. So there's 2 very important hooks in the Qualcomm image pipeline. One of them is after the debayering step, there is a hook into the compute DSP. This is so that the compute DSP can use hardware acceleration blocks for image dewarping and 3D perspective transform to do the night mode shots that your phone will do. So if you've ever played with a night mode feature, what your phone is actually doing is taking about 3 seconds worth of data along with the IMU readings, and then it dewarps every image, sometimes 50, sometimes 200 images. It will dewarp all of those, use the gyro data to correct the perspective, and then overlay those 50 to 200 images on top of each other to filter out all of the noise that you get in a low light environment, and then give you this really pretty image. Google was one of the first to do this on the Pixel 2, I believe, and the same compute DSP that they use is actually what's in our chip we use for image stabilization. So that's one very nice little hook. The much more easy to develop with hook is actually just called the raw data interface. And that's this one where the image processing pipeline can actually copy the images straight out of the imager front end. These are the actual bits that you get out of the sensor. Nothing has been touched by the ISP, and that goes straight into the Linux application processor accessible memory. So there are some advantages of using that whole pipeline. You can get very, very low power image streaming, and so we use that for streaming to Q ground control. If you buy any of our development kits, power them up out of the box and connect your laptop to its little soft AP and open Q ground control. Q ground control will automatically connect and the video stream will pop up in the bottom. You get the Mavlink enabled record snapshot button and record video buttons all pop up in Q ground control automatically thanks to that Mavlink camera interface protocol. So that uses the whole standard Qualcomm image pipeline. That's very, very low power. It's very, very low latency. It's kind of nice. And what's nice is Qualcomm give you kind of some out-of-the-box tunes and setups for the ISP. So we're using a Sony IMX412 on there. We recently got the IMX664 up and running as an experiment. And out of the box, they kind of look okay. You dial the white balance in a little bit and kind of good to go. However, there are some limitations. Lens shading correction is another one. We have to go through a process for every one of our lenses where we aim a camera at a flat gray wall just like this. And then we have a little MATLAB script that calculates out what the lens shading is. For those of you not familiar, if you have a very wide angle lens, the light which comes into the lens and is then refocused onto the sensor does not actually impact the sensor perpendicularly all the way across. If you have a very wide fisheye lens, you actually have an angle up to sometimes 20 degrees where the light is actually hitting the corners of the sensor at an angle, and therefore the sensor does not pick up, is not nearly as sensitive. And so you have this very dark shading out toward the corners. And that's something that the Qualcomm ISP corrects for very, very early in the pipeline, sort of in the debayering step at the same time. You have this lookup table. But this is annoying to take that data and then put it into the Qualcomm format. Another issue is your phone is really only ever set up to have two cameras going at once. You may not realize it, but oftentimes there'll be a second camera going so that you can quickly toggle between the two image streams. That's also used for the perspective shift. If you are in portrait mode and you see the person's face looks really sharp and then it kind of blurs the background, it's sometimes using two cameras at once with a little bit of depth from stereo to figure out where people are. That's for phones which don't have time-of-flight sensors for autofocus and mapping. There can also be a lot of delay there when you're doing the highest quality processing. So for example, when you take a snapshot on your phone, that may take like half a second in the background for the ISP to actually do a full pipeline and then compress the JPEG and save it. If we're just looking for low latency, you can't use all of that imaging processing pipeline. So something that we've been working on internally is what we call the MISP, or the ModalAI ISP, which is our own software stack to replace and complement the Qualcomm ISP, but it runs on the GPU. Now, luckily, we can allocate memory on this chip, which is accessible by both the GPU and the imaging pipeline. And so what we do is we reuse Qualcomm's imager front end. On this chip, we can actually talk to up to 7 cameras at the same time. And so 7 different real-time MIPI interfaces are buffering data from the cameras, saving it into memory, and then letting us access it. That's either in 8-bit, 10-bit, or sometimes even 12-bit format. From there, we go into this kind of dual GPU and CPU architecture where we try to offload as much onto the GPU as possible to do things like the lens shading correction and image stabilization. We can even do digital gimbaling, where without having to have a physical, heavy, power-hungry gimbal on the front of a drone, we instead just have a very wide fisheye lens, and then in our GPU software stack, we can have the user pick what region of that fisheye field of view they want to look at, and then we just do a digital gimbal all in software. So Once that has been processed by the GPU, we have this chunk of raw data, and that same chunk of memory we've also made accessible by the Qualcomm video encoder so that it be quickly compressed into H.264 or H.265 and then shipped out to the ground station for the lowest latency video possible. So, a couple of specs here. We have just an image stream going over RTSP. This is the same sort of video stream that you'd look at it in VLC or Q ground control. And so we don't have enough contrast here to really see it. So we're using 2.7% of the GPU right now to do this 720p video stream. That's all of the lens shading correction and the video compression going. And as part of our voxel inspect cam tool, we can see the latency is 9 milliseconds. I think we've even gotten that down lower now. I think we found one more stray mem copy that we got rid of and took another couple milliseconds off of that. That is a good note to any embedded engineers who want to play with image processing on these little tiny systems, is the ARM architecture is so unbelievably fast. Especially for the big ARM A77 cores on this chip, that the memory bandwidth is your biggest limit. Like, a mem copy will kill you, but going through and doing lens shading correction on an entire image is just nothing. This is a nice little test of just seeing how much throughput we can get through. So we actually hooked up on one of these chips 4K cameras. And so this is doing video compression actually at 4K resolution, 30 frames per second on 4 simultaneous cameras. Just all running in parallel. This is how much GPU performance we have available. That is something we cannot do with the Qualcomm ISP, but we can do on the GPU. And that's H.265 compression as well. Okay, so that's kind of on the video streaming side. On the computer vision side, we have a very different set of requirements. Really what we're looking for is robust feature extraction in the world. For those not familiar with VIO or Visual Inertial Odometry, this is how we navigate indoors without GPS, purely off of visual features. And so the cameras are going to be looking for features which are normally sharp corners around the room, and then tracking them as the drone moves around. Now, through a process called homography and knowing the lens characteristics, we can now calculate where we've moved based on how those features are moving around in the camera image. So one thing you'll see on the left-hand side is just the raw data that's coming out of the camera. And the corners are extremely dark. This is the lens shading that I described earlier. This is a problem that every small lens has, where you have the lens very, very close to the sensor. Every single one of your phones has to battle this, and this is the big battle between the sensor manufacturers like Sony and onsemi and Apple and Samsung, who want to make the phones as small as possible. And so the first thing we can do is just apply some lens shading correction. So immediately now you've seen the corners, which were completely black, have now blown out, and now we can start seeing features. However, as you're flying around in the room and your exposure has to change to account for different lighting, or perhaps somebody flicks off the light switch and now the camera suddenly got dark, we want to provide our computer vision algorithms with the most stable, smooth-looking video stream as possible. And so we apply a process called normalization to the image that tries to correct for exposure issues. This also helps, for example, when you're at the limits of exposure in a very dark room, and I'll show you some pictures of that on the next slide. And then the lower stream here, we just have the same images, but with a Fast9 feature extractor running, so that you can see how these dark areas will not be able to pick up any features. And then simply by applying lens shading correction, now we start to pick up features toward the corners of the frame. This is very important because the wider field of view that your computer vision cameras have, the larger the triangles are that it's using in order to triangulate its location in space, and therefore the more accurate the inertial odometry can be. Okay, so this is our very unique image normalization method. A typical normalization method, you'll kind of do a histogram of the image and then look to see, okay, what part of the 8-bit range between 0 and 255 are we looking at in this area? Is it underexposed or is it overexposed? You look at the limits and then you'll just sort of linearly stretch out all of the pixel values to try and cover evenly the 0 to 255 range. We do something a little bit unique. This was a method that I thought of where we take the original image, we downscale it to 1/20th of the size. So we have this really tiny little image and then we blur it to make it even fuzzier. Blow that back out to the original size, and then what you end up with is just a really blurry version of the original image. Now, if you divide the original image by the new blurred image, what you end up with is one new image where the mean pixel value is 127 right in the middle, but it's done that normalization based on the ambient light in different parts of the image. And so you're kind of normalizing the dark regions as the dark regions and the light regions as the light regions, but you're doing those based on the physical location in space, not based off of any other pixels in the camera frame. So no part of the image is affected by another part of the image in the other room. So this is the benefit of preserving local contrast linearly, which means you can dial up and down the gain as much as you want, and the image will look the same in the normalized stream. You can also have a glare of sunlight come through a window and saturate part of the image, and the opposite corner will not be affected at all. So this is perfect for visual inertial odometry. This also gives you the advantage of using the 10 and 12-bit raw data from the sensor originally. The vast majority of computer vision algorithms and stuff that you'll find in OpenCV wants to use 8-bit images. And so if you're converting to 8-bit first and then doing your normalization, you've now lost all of that extra dynamic range. So this is what happens if we try and do feature extraction in a dark room. I just put my drone, that one I just passed around, in our storage closet with the door closed. And I left the door open a little bit with the sunlight coming in. So there's another window over here, and so this area is extremely bright, covered in sunlight, and then this area is a basically pitch black room. And you'll see we pick up a couple of features off of LEDs from our server rack, and then tons of features in the sunlit area. As soon as we apply normalization to this, boom, features everywhere. For reference, this is accelerated on the Compute DSP on this Qualcomm chip. So the Compute DSP has hardware blocks for image pyramiding, Fast9 feature extraction, normalized cross correlation, optic flow, lens shading correction, dewarping, 3D perspective transform, and depth from stereo. All of that is accelerated in the hardware with special little blocks which use almost no power. So the different colors you see here, these are Fast9 features that were extracted on 3 different pyramid levels. So you can run voxel test feature extraction as an app in our SDK if you get any of our development kits, and it just spits out this live video stream in our web portal. So the big blue boxes are on the second pyramid level, so after the image has been downscaled twice. The green squares are on the middle pyramid level, and then the little tiny red dots are features that were picked up at the original layer. I like extracting features on multiple layers because you'll find rounded corners of things will not show up as a very robust feature that's easily detectable at the original resolution. But in very difficult environments, sometimes just downscaling the image and then picking up features or coarser features are enough to at least stay in the air and allow you to navigate. This is a little demonstration of the optic flow that's also running on the DSP. And so I'm just twisting the drone aggressively around in the air, and it's showing flow vectors all the way around. If you're looking at these slides later and trying to pick this out, notice that's actually a propeller that's in the field of view of the camera, and so that's why there's no flow or minimal flow vectors around here, basically just the noise. Okay, so what do we gain from all of these performance improvements? Well, we've been working a lot on the OpenVins project and pushing a lot of commits back. OpenVins is a GPL open source visual odometry system. We've been working very hard to optimize it to run on embedded systems. And a lot of that is just to do with getting it to run on multiple cameras at once. Why run on multiple cameras at once? So you have fewer points of failure. If one camera gets blinded by the sun or is looking at a blank wall, you need other cameras tracking features to be able to stay in the air. So out of the box, even after a lot of optimization and crawling through the code, but still using the OpenCV feature extraction and tracking, we'd be running about 21% of the CPU when the drone is sitting still, and then once you start exciting the features and actually doing some compute and feature tracking, we'd be up to almost a third of the CPU. I don't like this. We're trying to make development platforms for you to run your fancy algorithms on. VIO should just be a background process giving you data for free. And so our next step was to try running a feature tracker on the DSP using the tools that we have before. And immediately that cut down to about 2/3, a little bit less than 2/3. We still have to optimize the rest of OpenVins out, but we want to start the big computer vision side. Recently, actually as of yesterday, we now use a GPU accelerated feature tracker as opposed to the DSP accelerated feature tracker, which uses a little bit more power, but is lower latency and gives us more control over the algorithms. We can write our own OpenCL kernels to be able to fine-tune the process. And so we use slightly more CPU actually in flight, nothing too significant, and about 20% of the GPU. By the way, all of these numbers is not just the OpenVins process. This is the entire camera pipeline running, capturing, buffering all of that data, and then transporting it between processes. We still have a lot more to optimize out. Our next main release is focusing on latency and reducing mem copies, and so we've figured out a way of passing raw image data around between processes without mem copies, just by allocating memory in such a way where we can pass by reference between processes. So I expect that to cut down another 3–4% CPU once we've got that released. Okay, are we going to get my video coming up? Nope, button stopped working. Yay, there's the video. So I brought the drone and some batteries so we can actually fly around in the offices if Firestorm will let me, if you've got a little safe flight area. So here's a little video of me flying around the office showing the features that are being tracked across all 3 cameras. So this is nothing special. This is all our open source SDK. You can buy the PX4 autonomy development kit, which is a version of that drone I passed around, and run this out of the box and play with it and poke at the code, optimize for your specific applications. While this is playing, I wanted to discuss a little bit about the camera arrangement and why we've put the 3 cameras in this particular arrangement. We used to have cameras running at 45 degrees out the front when we had a monocular single camera system, because that fisheye out the front allows it to see some features on the ground and some features a little bit above the horizon. The next step up is to have one going forward so that as you're flying down a hallway, you're grabbing features off in the distance and then triangulating their location as they pass by you. But with a second camera facing straight down. This is very, very critical because in a monocular SLAM system, if you suddenly turn 90 or 180 degrees and lose sight of all of your features, you now no longer know where any of the new features are until you've translated. Cameras do not operate in 3D space. They operate in radial space. They only know angles to a pixel. They don't know distance. Until you start translating and moving around, then you can localize them. The advantage of a downward-facing camera is you're now able to track the same set of features that you've already localized through translation to that point. If you suddenly do a yaw motion, you've kept track of the same features, now you can start reversing back. So the downward-facing camera is very, very critical. The third camera out the back is kind of optional. It's a nice to have. I particularly like the front and back camera arrangement if you're doing very, very large lighting changes, for example, going into a dark room. So let's say worst case scenario, you're flying out in the desert sun and you're going into a pitch black bunker. As you fly through that doorway, the forward-facing camera is going to be completely dark and see nothing for maybe a second or so as the exposure readjusts and finds new features. If you have a camera out the back, you can continue tracking features outside with one exposure setting while the camera in front is readjusting and trying to see what's in the room in front of it. So I just did a little loop kind of around the office into a dark room. I did that 180-degree yaw maneuver in the near pitch black room. There are no lights on this drone, by the way, although you can add a little LED if you wanted to. And then I just tormented my colleagues, like flying under desks, which I love to do. And let's see if we can get out of this page. There we go. So things that are in the process of doing, removing more mem copies, just optimizing this process out. Our goal is always just to keep the power usage and the CPU usage as absolutely low as possible to free up as much CPU resources as possible for you to develop your fun algorithms with. And so that is it. Thank you very much for my little overview.
All right. Are there any questions for James?
Thanks.
So like open source versus what you sell, what's the distinction there?
So our software stack is open source. You can go to code.modalai.com, look through our GitLab, see all of our code. We monetize through selling hardware. We want to offer the smallest, lightest, most power efficient flight controllers possible and make the software developers' lives as easy as possible by just opening up everything for you to play with.
How much is that?
This is the top end unit with all the cameras and all the bells and whistles. I think this is $2,800, maybe $3,000. Yeah. And then the flight controller just by itself, once you start integrating into your own hardware, is $1,300. Yep. Yep.
Yeah, we have one of the Starling 2 Maxes that we've been using, and we've noticed when we were using VIO inside sort of a dark warehouse, pretty, nondescript walls, it sometimes loses its traction, and it looks like it's only using one camera. So I wondered if that multiple camera VIO is available. If maybe we're doing something wrong. I just want to make sure it's working.
You're probably running an Auto SDK. When we released the Starling 2 and the Starling 2 Max, it was still using the old monocular SLAM algorithm. It was like 4 weeks ago we released the DSP accelerated OpenVINs that enable both cameras, and then it was just yesterday that we released the triple camera GPU accelerated. So yeah, this has been in progress for years now, and now it's finally polished and released.
Can't wait to